not going to be it.
Two restaurants of morning, so I didn't get paid like a single minute your guys' if I had a choice, I would know it was terrifying. The other team had these like people who were really large. We like slaughtered them. It was like 48-18. Yeah, I scored 0. The rim a couple times. But you can, okay, we have one that is like, okay, what did that?
Yeah, if it was simple, we wouldn't do it.
It's like,
But the good thing is,
yeah, and so they like move this down to like.
I doubt our tournament.
It was like nice outside. It was really fun. No, yeah, it was really fun. They like to exactly like they were very serious. Like the other team was like it got to the point where they would score a basket and they just went like crazy. I don't know, they're not really. They have some kids who like really play sports and then well, you're yeah, that's right.
Like I wrote about that.
I don't think the other teams like when I just watch them. As soon as I get on, they're like putting them in like whoever your guy goes on basket. Yeah, like the other team had a lot more than one girl, but like
I got to hear.
there's one girl that I was starting with. I don't know.
Well, I couldn't figure it out. I did like 3 pages.
Like, we ended up having to guard a guy sometimes, but that was like traumatic.
Yeah, wait.
I know. Sometimes there's this girl, but we don't know where she's from. Some like girl who like ended up playing on the team last night. She's like grade 5, tiny, and she's really good. Yeah, she's like really quiet. And then she like scores.
Tried that first. I wouldn't count for it.
So I would
Yeah. Well, because I talked to, well, one of the people I talked to said that he went to
I realized it, and I think I
Okay, you guys, we're going to continue with section 7 today. Just let me remind you of a few things. First, let's see. The web work from section 7 isn't actually due until Friday, so that was intentional. And the start problems are due Friday. I'll get those start problems graded and back to you, and if you want them, you can get them Sunday evening at the office hour. Today we continue section 7. Friday, a web work review opens up, and that'll be due, I want to say, by 5 o'clock. It's not due at all, but it'll close at 5 o'clock on Sunday. And then I pointed out to you already the many solved problems. So if you're looking for some extra problems to do with solutions, there is that. Friday in class we'll just do review, group work kinds of things on not just section 7, but in fact on the entire chapter 15. I guess that's all I have to say. Any questions before I get going? Okay, that works. Happy Halloween. I will continue today to try to develop the qualitative motivation for this change of variables theorem, and then we'll finish the period just by doing some problems. I'll do an example, you'll do an example, I'll do one, you'll do one. We'll see how it goes. Okay, so where were we? Let me remind myself. Okay, so last time, the thing that I was trying to motivate last time was when you have certain change of variables, like that can be represented as a matrix, then there's this really nice relationship between the determinant of the matrix and how the matrix changes area. And what we discovered was the determinant is precisely the correct scale factor for the area. So if the determinant of a matrix is 2, then it's going to double the area of a set as it goes through the transformation. And that was the point that we were trying to make last time. So from last time, we saw that the determinant of t is the correct scale factor for the transformed area. And if you'll remember, we had the UV plane and we had the XY plane. And we were taking little figures here, and they were sort of getting sent over here by some transformation. And for this transformation, I think that the determinant was -1/2. We took the absolute value, and so what we saw was that the area was being halved. What I'd like to try to do is motivate, for some of you that have read and perhaps worked on some of the problems, you've run into this thing called the Jacobian of the transformation. And the Jacobian is similar to this determinant thing. And in fact, for simple transformations like the one that we were talking about on Monday, it is exactly the determinant. But for more complicated transformations, the Jacobian means something else a little bit. And it's motivated by this. What I wanted to do before I went into today's finalizing of this change of variables theorem is I want to recall let's recall some stuff from Calc 1. And I want to look at a function. Let's do something like that. Yeah, maybe a little bit even more dramatic. So dramatic. Okay. So here's a function, just a regular old function, f. Nice, smooth function, increasing. What I want to do is I want to see how this function transforms intervals. So if I take a little interval here and I push it up through the function and it pops out the other side, what do you notice about the length of that interval? The length of what comes out versus the length of what went in. It's stretched out, right? It's stretched out. On the other hand, let's go out here. And let's push this guy through F. And we see that the transformed interval is smaller. So up there, it gets compressed. So down here, intervals get stretched out. Way out there, intervals get compressed. What do you know about F that will predict that compression or expansion? The derivative, the slope, exactly. So the larger the derivative, the steeper the slope, the more stretching occurs. The shallower the derivative, the closer the derivative is to 0, the more compression there is. And where's the break point? Where do you go from compression to expansion or stretching? When the slope is 1, you have precisely, area or length, I should say. Length is preserved as it goes through the function f. But if the slope is larger than 1, then length is stretched. And if it's less than 1, then it's compressed. There's also this little issue that we explored last time about the sign, S-I-G-N. What does the sign of the derivative tell me? What effect does that have on the interval? Exactly. So if it's negative, then f is decreasing, and it's actually going to take that interval and flip it as it sends it through. So it'll stretch it or compress it, and it'll also flip it. So what we see is a direct analogy to the stuff that we were talking about on Monday with the determinant. We saw that the determinant told us how much area was stretched or contracted, and that the sign of the determinant told us whether it was a mirror image or not. So there's definitely something going on here. There's a link here. Okay, what's weird about this thing, let me rewrite this in a slightly different way. Okay, so over here we had a little guy, and it went to a big guy. Like that. And out here we had a big guy, and it went to a little guy. Oops, not good. This is a different way of looking at what f does. Okay, so every point on the real number line ends up somewhere over here, right? And some points are being stretched out as they end up over here, and some points are being compressed together as they go over there. And what we talked about, and this is a different way of looking at f, this is still just f. What we talked about was that compression or expansion depended on the derivative of f. So these are two pictures of exactly the same situation, just two different ways of looking at things. The reason I drew this second one is I want to compare it to what we were doing on Monday, where we had two planes instead of two lines. And we had a little box. And over here it went to, an even smaller box like that. Like that. These are really two very similar processes. The only difference between what f is doing and what t is doing is f is drawing from this number line and sending things over to another number line. And here t is drawing things out of a plane and sending things over to another plane. This way of looking at functions is this is the mapping perspective. And I really like talking about and thinking about functions from this perspective. It's a very geometric way of thinking about functions that's different, I think, than what you're used to dealing with. And what's really interesting about this, and this is stuff that you would study in other math courses, not Calc 3, what's really interesting is the way that the calculus of these functions, derivatives, integrals, and so forth, interact with the geometry of these pictures. It's really interesting to look at some of the connections, some of the parallels. Okay, so if the derivative of f in this picture tells us about stretching and contracting, the same thing is actually should be true about the derivative of t. So what we've kind of been hinting around here is that derivatives describe local stretching and local contracting. Why do I use the word local here? I use the word local because whether you're in a region that gets stretched or whether you're in a region that gets compressed depends on where you are, right? What we noticed about T from the example Monday is it didn't matter where you were. If you had a figure here and you mapped it over there, the area was shrunk, right? And we determined that that scale factor was 1/2. And if it was here, it shrunk by 1/2. If it was here, it shrunk by 1/2. Is that the same as what's going on up here? No. In the top picture, whether you get shrunk or expanded depends on where you are. And so it's a local sort of stretching or expanding. The difference between f and t is that f is a nonlinear function. Linear functions are uniform in the way that they stretch or contract all throughout space. All I was doing was writing. I'm going to try something. Sorry, guys. This computer has been not very... Okay, Task Manager, here I come. Control-Alt-Delete. Time to kill OneNote. Gosh, I have no idea even what OneNote is called. Maybe it's called OneNote. Yeah, I'm looking at the process list. There we go, OneNote. Okay. End process. Okay. It's dead to me now. I seriously have to figure out how to do all this in Linux. Yeah, I hate Windows. And yes, I'm recording that. That's for you, Bill Gates. Whatever came with 1204. Ubuntu 1204, hold on, view, almost there. That's good, that's good. See how much of it I lost. Not too bad. Okay. So linear functions, let's see if we can't. Stretch oops, misspelled stretch, compress uniformly. Nonlinear functions can compress in some areas and stretch in another area. Wow. So annoying. Sorry, here we go again. At least I know what I'm doing now. And if it happens again, there's always chalk. Say it ain't so. OneNote. Die OneNote. Die very hard.
Is it Office?
Yeah, it's part of Office. Yeah. I'm sure it's some Microsoft update that's supposed to make our lives much better. All right. I do, yes. Okie dokie. I'm done making this point. I'm not writing it again. Okay. Moving right along. View, full page. Okay, what was I going to do next anyway? Okay, so nonlinear functions can stretch locally in one place and compress in another place. The nice thing about nonlinear functions, yes, I'm afraid to write on it now. The derivatives have local behavior described by their derivatives. Okay, and that's kind of what we were getting at with this picture up here. Right, we saw that stretching occurred in places where the derivative was bigger than 1, and compression occurred in places where the derivative was less than 1. So actually all is not lost here with respect to this derivative describing compression and expansion. And we can use this idea in the change of variables theorem. The derivative, let's say we have a transformation T. The derivative in this case which we denote T prime, is a matrix. And I'm not going to prove that, but it's a matrix of partial derivatives. And for example, if T goes from R2 to R2, in other words, from the plane to the plane, then it's a 2 by 2 matrix. And in fact, it's this 2 by 2 matrix. Let's say that T is described by two functions. T of u and v is f of u and v, g of u and v. If T is described by two functions like that, and don't worry about the gobbledygook, it'll clear up in a minute. Then you can take these partial derivatives. the partial of f with respect to u with respect to v, the partial of g with respect to u with respect to v. You put them in this 2 by 2 matrix. And what this tells you is the determinant of t describes the local stretching and compressing. What do I mean by local? At a particular point, right, you pick a point u and v and you compute this matrix. If the determinant of the matrix is bigger than 1, then at that point, t is stretching things out. And if I take another point and I compute that matrix and the determinant is less than 1, then at that point, it's compressing things together. And this works for linear functions where it's always stretching or always compressing, and it works for nonlinear functions where over here it's stretching, over here it's compressing. Why is this useful? Because the integral only cares about local stuff. Consider a little dA, a tiny piece of area. When you take dA and transform it by t, the area gets scaled by the determinant of t prime. So this whole discussion is really trying to motivate what many of you have seen in the reading and in the exercises, why it is we introduce this factor here when we do change of variables. It's because that factor describes what's happening locally to a little piece of area as it gets transformed by this transformation. Does the little area get stretched a little bit, or does it get compressed a little bit? And that absolute value determinant t prime is precisely the scale factor that you need. And in fact, it's so important that it's called the Jacobian. It has a name. And the Jacobian, for the 2 by 2 case, is the determinant of t prime, the absolute value of the determinant of t prime, which is really just f sub u times g sub v minus f sub v times g sub u. Absolute value of that. In the 3 by 3 case, it's a little messier. So in the 3 by 3 case, the determinant is different, and so you have to actually remember this separate case. That said, I'm never going to ask you anything other than 2 by 2, 3 by 3. So you only have to remember these two cases. Some of you may have explored this in high school with computing 3 by 3 determinants. And again, I'm not going to ask you to do this, maybe in homework, but certainly not on a test. The determinant of a 3 by 3 matrix, what you do is you rewrite it oops. And then finally what am I? I'm a dummy. Here we go. A, B, C, D, E, F, G, H, I. There. G, H, I, G, H. There. The determinant is you multiply along diagonals here, like that. And you add these to the determinant. And then you multiply along these other diagonals and you subtract those. So for example, the determinant of this 3 by 3 matrix would be AEI plus BFG plus CDH minus GEC minus HFA minus IDB. Very complicated, and not a formula that I want you to remember. The process, repeating the first two columns and doing these diagonal products, that's okay. You can remember that. But don't remember this as the formula. Remember the process as the formula. Greg?
Why doesn't the second right part have the C, the third column?
I don't know. Did I type it wrong or something? A, B, C, A,
I
B.
remember having a whole, like 32 matrices, so that's not.
No, it's just the first two columns.
Oh,
Yeah. Okay. Different processes, same idea. So the determinant is more complicated, but it yields the same results. Let me apply these two ideas to transformations that you're already familiar with. So let's look at the polar Jacobian. So in the case of the polar Jacobian, T of u and v is the following transformation. So I've changed r to u and theta to v just to keep it consistent with the notation that we're using. But secretly that's r cosine theta, r sine theta. So that's the transformation. The polar Jacobian then is the determinant, the absolute value of the determinant of t prime. Well, let's write t prime. So the first slot is the partial of f with respect to u. And the second one is the partial of f with respect to v. The third slot is the partial of g with respect to u. And the fourth slot is the partial of g with respect to v. Does everybody see where those came from? Let me note here, that's f, that's g. Like that. So those are just partial derivatives, all the proper partial derivatives in their proper place. Compute the determinant. So that's u cosine squared v plus u sine squared v, and it's amazing how often that Pythagorean identity comes up in this class. U cosine squared v plus u sine squared v is really just u. And we'll keep the absolute values there, and then we'll argue why they should go away. Now remember what I said when I started this. This is really r cosine theta and r sine theta. Playing the role of r here is u, and so what we see is that dA in the old coordinates becomes r dA, or r dr d theta, with absolute values around the r. We drop the absolute values on the r because r is distance from the origin. So they're there, but we can argue them away. And that's the polar Jacobian. Let's look at the spherical one. So recall that the spherical coordinate transformations look like this. Rho sine phi cosine theta, rho sine phi sine theta, and finally rho cosine phi. Now if I want to compute the spherical Jacobian, I've got to take the determinant of this matrix. X rho, x phi, x theta, y rho, y phi, y theta, and finally z rho, z phi, and z theta. That's a lot of work, and not even considering now the fact that I would have to multiply all this stuff together in the determinant, et cetera, et cetera. So I'm not going to make you do that, but I want to show you sort of the utility of learning some good computer algebra skills. How many of you guys are thinking about taking Calc Lab next semester? A few of you. Okay, that's what you'll pick up in there. You'll learn how to work with Maple and do some of these calculations using Maple, and you'll find that that'll be helpful if you really learn those skills well. You'll find those useful in other courses, especially physics if you're going to go physics. So let me show you how this is going to happen in Maple and just kind of convince you that the Jacobian that we've already learned, rho squared sine phi, is in fact consistent with the stuff that we're learning in this theorem. All right, so I'm going to fire up a piece of software called Maple, which is a piece of software that we use a lot in CalcLab. And you've seen me use it in here. Okay, and I'm going to define. First, I'm going to load a library that you don't. Yeah, let's do linear algebra instead. Okay, and I'm going to define the spherical coordinate transformations. Rho, sine phi, cosine theta. Y is rho, sine phi, sine theta. And z is rho cosine phi. So those are the transformations that we're used to. Stop me if you see a typo. And I'm going to build a matrix. I'll just call it A. I'm going to build a matrix of partial derivatives. So the derivative of x with respect to rho, the derivative of x with respect to phi, and the derivative of x with respect to theta. And I'm going to make that the first row. And then I'm just going to change the x's to y's and then z's. So y, z. And if I run that, it doesn't look like anything that you're used to seeing in terms of a matrix. But if you look carefully, here's the first row. This is the derivative of x with respect to rho, and that makes sense. This is the derivative of x with respect to phi, and that makes sense. And if you go all the way down, you see a 0 sitting here. What's that 0 coming from? That's the derivative of z with respect to theta. You'll notice there's no theta in z. So that's at least a sketchy, hand-wavy thing that Maple is actually doing the right thing. Now if you do the determinant of this matrix, which Maple knows how to do, it's messy, right? And that probably looks a lot like what you would get if you did the diagonals, multiply the diagonals, add them, multiply the other diagonals, subtract them, etc., etc. But if you simplify, you get rho squared sine phi. And this is an extremely powerful theorem because instead of wrestling with the geometry, which I really didn't do when we did spherical coordinates, but instead of like looking at these little pieces of volume and seeing how they change with respect to the variables, or thinking about these little sectors in polar coordinates and how they grow and shrink as they move towards and away and towards the origin, I can dispense with all that now. Now I have a machine that's going to calculate these scale factors. And the machine works in the two instances that we're comfortable with, that we already know. And I'm using that to convince you, it's not a mathematical proof by any stretch, but I'm using that to convince you that this machine now works in any case. Any linear transformation that's sufficiently nice, which for our cases is pretty much everything you'll run into, this is the way you find the scale factor. You populate this matrix, you take its determinant, you take the absolute value, and you're done. It's an extremely powerful theorem. And as I mentioned, it took, I think, a week for me to prove it in graduate school, to prove the change of variables theorem in graduate school. Okay, so enough about that. Let's go and do some actual problems. So what I'd like to do first is just compute a Jacobian for a transformation that that you haven't seen before, and just so that you get an idea of what the process is. Okay, so our first example is simply to compute the Jacobian for this transformation. X is equal to e to the s plus t, y is equal to e to the s minus t. And yeah, this is a transformation that you might run into in differential equations, for example. So to find the Jacobian is really simply a matter of taking the absolute value of the determinant of this matrix. And the matrix is the partial of x with respect to s. What's the partial of this thing of x with respect to s? It's the same thing, right? It's just e to the s plus t. And with respect to t is the same. And now we do y with respect to s. And the last one is the only mildly interesting one. You introduce a minus sign when you take that derivative. So is everybody comfortable with those partial derivatives? So that's the partial of x with respect to s, x with respect to t, y with respect to s, y with respect to t. What do we do now? We multiply diagonals and subtract. So e to the s plus t, that's a negative e to the 2s, looks like. And then the diagonal, the off diagonal, e to the 2s. And that looks like 2e to the 2s. So the Jacobian, in this case, is 2e to the 2s. Just a technique. When you're doing these determinants, especially the 2 by 2, just put a minus sign and then do the product of the off diagonal here and then distribute, and just so that that'll make it less likely that you'll make a sign error. It's hard to keep track in your head. So the Jacobian here is 2e to the 2s, so if you were doing this change of variables in an integral, this 2e to the 2s would appear in your integrand. All right, let's do a more complete example. Exercise 1577. Whoops. Okay, so 1577. I'd like to evaluate this integral over the region bounded by these four curves using the following transformation. This is the first time we'll have done a problem like this with a fully nonlinear transformation. All right, let's write this out. So we have y times sine xy. Oops, no comma. Y times sine xy, and x is u over v, and y is just, oh goodness gracious, was it u? I can't remember. Y was v. Okay, there's the transformation, and then the region that we're interested in is the region bounded by all of these curves. So xy equals 1, xy equals 4. And then Y equals 1 and y equals 4. I suppose the most, I guess you can do this in a lot of different ways, a lot of different orders. Let's do the Jacobian first. So we'll take the determinant of the matrix of partial derivatives. The partial of x with respect to u is just 1 over v. What's the partial of x with respect to v? A little trickier. Not ln. Great. Negative u over v squared. Partial of y with respect to u, 0, and with respect to v, 1. That's pretty easy. Okay. Jacobian is just the absolute value of 1 over v. And we might be able to drop that absolute value at the end depending on what the limits are on v. So if the limits on v keep v positive, then we can drop those absolute values. Okay. This looks pretty scary. We've got this really complicated region in the xy plane, and not only is that region complicated, but we've got to figure out where it came from under this transformation, which is a fairly daunting proposition. Let me show you how it's not as daunting as it may seem. This is actually a nice situation. When you're given the equations of the curves that are bounding the region of integration, you can actually use the transformation substitution to get curves in the new variables. So what do I mean by that? So x is u over v and y is v. So x times y is u. And so what we get is, instead of xy equals 1, we get u equals 1. And what we've learned is that under this transformation, this curve came from what line? It came from the line u equals 1. U equals 1. U equals 1. Okay, so just substitute x equals u over v, y equals u into these guys to get curves in the UV plane. All right, well, so let's do that one by one. So we've got 1, 2, 3, 4. So for 1, we've just learned that that's u equals 1. 2, u equals 4. 3, v equals 1. And finally 4, v equals 4. Thank you. So we don't even really have to we don't have to sketch this now. We know that this original region is transformed back into just a box. U equals 1, u equals 4, v equals 1, v equals 4. Is everybody still with me? So the new limits of integration, and in fact it doesn't even matter what the order of integration is. So I've got the new limits of integration. What happens to dA out here?
Turns into dA over v.
1 over v. I can drop the absolute values because the range of v values that I'm considering is positive. And the last thing is to transform the integrand. So we already know what x and y are in terms of u and v. Y is v, and the sine of x times y is sine of u. And the niceness just keeps coming. The v out front cancels with the v from the Jacobian. And I end up with a fairly straightforward integral. And in fact, this is, I can actually do the v integration. That's 3. Times sine u du. I'll let you finish it off. Let's do another one. In fact, I'm going to give one to you. So you guys work on this one with your usual partners. 15.7.6. Get rid of that thing. 15.7.6. So your job is to evaluate this integral over the triangle with these corners using x equals u and y equals u times v. And following my example from problem 7, what I'd like you to do, I know on Monday what we did was we took those points and we figured out where those points came from. Now I want you to look at the curves that connect those points and figure out where those curves come from and use that approach. That's actually a safer, more robust way of doing things. So for example, this is a triangle, right? There are 3 curves that describe the boundary of this triangle. Y equals 0, x equals 0, and y equals x. Yeah? 4, sorry. Yeah, x equals 4, y equals 0, and y equals x. So use those 3 curves to figure out what the new region looks like. And I'll let you work on that for 5 minutes, and then we'll bring it back together. So find the Jacobian, find the region, transform the integral. All right, you guys, let's bring it back together here and see where we're at. Okay, so in the xy plane, we're looking at these points and this triangle. Get these three curves. So what's the curve? We've already discussed this, but what curve describes 1? Y equals x, good. And 2? Yeah, 2 is y equals 0. And 3, let me just put 3 over here, is x equals 4. Does everybody see that? And let me remind you what the transformation was. X equals u and y equals uv. And let's just go around the figure here and figure out what these curves look like in the UV plane. So for problem 1, we have UV is equal to U. Either, there are two possibilities here. Either U is 0 or V equals 1. And both of those things are important to note. It's not just one or the other. Make sure you write down both of them. Let's go to the next curve, 2. We have UV equals 0. Two more solutions, right? What are they? U equals 0, V equals 0. Okay, and let's finish with the last guy here. X equals 4 is U equals 4. So that's pretty straightforward. And what you have to do now is essentially go around and plot all of these curves that you've come up with from this process. So all of those guys. All right, so I'm going to get my hands on a UV plane. And let's go around the horn and plot all of these guys that are underlined in red. U equals 0 is this stretch here. V equals 1, this stretch here, right? You have U equals 0, which we've already done. We have V equals 0, which is this stretch down here. And finally, we have U equals 4. 1, 2, 3, 4. That's this guy here. Now, you don't really know in advance what's going to happen, what kind of figure is going to be traced out. So that's why I kind of drew these things out really long, and I just let them intersect with each other wherever they're going to intersect and figure out what that region is going to be. I didn't really know where it was going to be. Andy?
It doesn't particularly matter if U or V is on the vertical or horizontal axis, right?
No, not at all. Not at all. Okay. So we see the region here is 4, 1. Again, this transformation isn't the way it is by accident. It's this way because it makes things nice. So it took this triangular region and turned it into a rectangular region, easier to integrate, presumably. Okay, so that's the region. What about the Jacobian? What'd you get?
1, 0, doesn't matter anymore.
So 1, 0, and what? V, U? Is that what everybody got? Good. It looks like on this region of integration that the absolute values don't matter. So we can drop the absolute values. Let's integrate with respect to v first. So if we do that, what are the limits in v? 0 to 1. And if we then do u, that's 0 to 4. Okay. Out here, dA is u, dv, du. Right, where did that u come from? It came from j. And last, we have to transform the integrand. And the integrand was the square root of x squared plus y squared. So that's the square root of x squared is u squared, and y squared is u squared times v squared, square root. So that's the integral. Okay? And now it's just a matter of doing it. Let me clean this up in a way that might make things easier. Oops. So I did a lot of algebra there. First of all, I noticed that there was a common factor of u squared, which I pulled out, and that turned into a u. But then that u joined forces with this u to give me a u squared. Then I noticed that the integrand was separable, which means I can take the double integral and write it as the product of two single integrals. And I take all the u dependence and put it on the left, all the v dependence and put it on the right. The left-hand integral is fairly easy. The right-hand integral, meh. Do you know how to do that one? Yeah, Wolfram does, but what if you don't have Wolfram?
Trig sub.
Yeah, it's a trig sub. Yeah, you happen to know which one for extra credit? It's not sine or cosine. Yeah, it's secant or tangent. Sorry?
This is why we ask Wolfram.
Yeah. Anyway, so I'll stop there. We don't need to dwell on the trig sub. Okay, let's keep going. How about this one? Yeah, put you to work in the last 10 minutes here. Yeah, find this integral. And we're going to let x equal the square root of 2 times u minus the square root of 2/3 times v. And y is going to be the square root of 2 times u plus the square root of 2/3 times v. Yeah. See what you can do with that. So see if you can find j, and then see if you can figure out how this transformation transforms this region just by direct substitution. And then notice that if you do the direct substitution here, don't do it again because it's the same thing here. Okay? See if you can figure that one out. And I'll do the same. So this transformation does do a nice thing. So if you're doing your arithmetic correctly,
Be nicer if it was 2x.
actually, well, yeah, but it's not. I guess for the sake of time here, what are you getting for J? I can show you what I got for J. So I got 4 over root 3 for J. What about, what happens to x squared minus xy plus y squared? Where does that look like? Did anybody get that?
She said u squared plus b squared is 9.
Close. It does get rid of the xy term, you're right. I got 2u squared plus 2v squared. So you can check that. So it took this ellipse that was like this, and it turned it into a circle of radius root 18. And that same thing happens to the integrand. The integrand turns into 2u squared plus 2v squared. So check your algebra. It's nothing more than substituting in x equals that, y equals that, expanding it out, canceling terms, and out pops this thing. And in fact, that's the motivation or the whole reason for this transformation, is that it takes this slanted ellipse and turns it into a circle. Once you do that, the region is a circle, the integrand gets simpler, and you're left with an integral that you can do. Don't forget to throw that Jacobian in there, onto the dA. Otherwise, you're gonna be off by a factor. Play around with that one. Maybe I'll put it on the review sheet for Friday. Friday, we're gonna come in and we're gonna do review for the whole chapter, not just section 7. But I will start off with answering questions about section 7. See you then. Happy Halloween. I don't know what it is. Oh, nice. Yes, it was quite appropriate. Never wear that again, please.